Today's webinar on steel connection design using RISAConnection design is going to be featuring our latest product, RISAConnection. And I'd like to point out right from the start that this will not only be an informative webinar showing off, the features of RISAConnection, but you can really look at this as an actual training on how to use the product as well. So first off, let's just take a look at what overview we're going to be talking about today. Well, we're going to be talking about, what the program is and what it's capable of. We're going to talk about the shear and moment connections that have been integrated into it. We will talk about the design process, and that is just the overall process of using the program. And then we'll talk about what's next for this program. So overall, what we have here is shear connections and moment connections built into RISAConnection. Now this is version 1.0, and you should bear in mind that version 1.0 is just the beginning for the program here. So while you see what we cover today, this is just the very initial set of offerings. However, we do have a very aggressive development schedule planned for RISAConnection, and we have many additional connection types that are in the works and on our to-do list. To begin with, though, let's take a look at what RISAConnection has in it today. You have the capability of doing wide flange shear connections using clip angles, shear tabs, end plates. You also have the capability of putting beams to girders, column flanges, or column webs. Now moving into the moment connections, you can see we have two primary types of moment connections here. We have the flange plate, and we have the end plate on here. So these are just the basics of the RISAConnection moments that are available in there at this time. Now, I know that I'm going to get a lot of questions right off the bat about, okay, where are the HSS connections? Where are the seismic detailing connections? Where are the bracing connections? And I want to point out that all of these connections that you're mentioning are in the works, and we plan on adding these connections to the program over a series of updates. Now, let's continue into the program and take a look at it. So what I'm going to do is I'm actually going to come here and launch RISAConnection. And let's fire this up here. And so you can see that when you open up RISAConnection, you're going to get the same sort of starting a model pane that you would get in RISA 3D or any one of the other RISA programs. And what I can do here is I can click on this button here to create a new project. Now this is where I should point out the difference between projects and connections within RISAConnection. A project is essentially a model file containing multiple connection designs within it. So therefore, for example, if you were working on one building, you could actually put in all of the connections for that building into one project and open it up and keep them together in that way. In that respect, you don't have to juggle a large quantity of files back and forth when you're saving all of your different connections for that building. Now, when we come in here under Create New Connection, you can see there's two ways to choose what our connection type is. On the left here, we have a tree that I can choose from, where I can choose whether I want to do a connection to a column or to a girder, and I can choose whether my beam connection is going to be done using an angle, an end plate, an end moment plate, so on and so forth. Otherwise, if I go to all modules here, on the right I get graphic depictions of each connection type that's available. Now for this first example, and we're going to go through several examples today, we're going to take a look at the girder beam clip angle shear connection. And what I can do is I can give this its own connection name, and so I am going to call this the girder angle connection. And this will allow me to identify it as I'm going through the project. And I want to add this to my current project. So I'm going to go ahead and hit OK. And so the first thing we see is in the Projects Explorer in the upper left corner, we see my girder angle connection created. And we see one connection listed here under the project view. And as we add more connections, we're going to see additional connections appear in here. Now, before we get into designing this connection, let's take a look at the interface within RISAConnection for a moment. If I come up here under File, you can see all of the standard options, including an append option. Now, the append option would allow us to take multiple projects and append them together into one project. So if I have many different connections that I want to put into a project, I can use this feature to do so. The other settings are all typical Windows settings available: New, Open, Save, and Save As. Moving along, under Edit, we have Undo and we have Redo available. Now let's move on to the Global menu. Under Global, if I click on here, this should look very familiar for those of you who are RISA 3D users. And so let's give this project a title. So I'm going to call this the Webinar Project. The company will be RISA. The designer will be myself. We'll just give it a job number, and we'll give it some notes. And we can put this in here so that when we print anything out from here, we can actually have this information available, and we can also keep track of information that's on this project. So now I'll move over in the Global Parameters to the Solution tab. And the global parameters are going to affect how things are designed and handled within RISAConnection. So when we take a look here, we can choose the design method, ASD and LRFD. Now, some of you may be asking what code this is going to be under. The first release of RISAConnection, version 1.0 here, comes with the 13th edition AISC steel code. That's the 2005 AISC 360 code, to be specific. So currently you can choose between ASD and LRFD on there. So I'm going to choose ASD in here. Now for the bolt group analysis method, this is going to determine how the strength of the bolts is going to be calculated when there's an eccentric load on a group of bolts. And we're going to go with elastic on this one. For the weld analysis method, we can also choose whether we're going to use an instantaneous center of rotation method or an elastic method. And I'm going to start off by using the elastic method for today's webinar. Now you can see here we can also choose whether or not we're going to consider bolt hole deformation. Now you might be wondering, okay, how does this bolt hole deformation affect my connection design? Well, we've written up a help file, and if I click help here, it's going to take us immediately to a description in the help file of what we're looking at. And if I scroll down farther, I can take a look here and see consider bolt hole deformation. This checkbox defines whether deformation at bolt holes at service load is a design consideration or not. And this impacts the bolt bearing strength equations. And we can actually go to the bolt bearing strength topic to get more information. And here you get all sorts of background on all the calculations that we offer within the program. We'll come back to the help a little bit later as well, but as you can see, we've extensively documented all of the checks and assumptions that have been made in the program here so that you can easily come through and review exactly what the program is doing. Our intention has been to make RISAConnection as transparent of a program as possible to make it as easy for you, the designer, to verify the numbers and confirm things in it. Now, I should also point out that RISAConnection has been designed for structural engineers. So a lot of aspects of other connection programs that may be specifically aimed towards detailers have been left out. And that has been intentional because it helps streamline the input process. Obviously, such factors as how long a bolt are or how many washers go on a bolt aren't really going to impact the engineer, and so you don't want to have to sit there and enter all that information in. Instead, if you just enter in the basic engineering properties of the bolts that you would use in any hand calc method, that will be enough for us to give you your engineering design. So I'll hit OK and close out of the global parameters, and let's just move on a little farther here. If we go to the units, you can see that we can control all the units here, and this is all the same setup as RISA 3D. I'll close out of here. Under View, we have 2D and 3D views. We'll come back to that in a moment. We can add or remove connections from the program. We can also come in here under Tools and Preferences, and we can set up a number of different preferences. And we'll come back to these as well. So let's go ahead and take a look at the interface of the program. So to do that, I'm going to open up this girder angle connection that we've created underneath the webinar project. And when I open it, what you'll see is this connection opens up in a 3D view. And in this 3D view, if I hover my mouse around, I can actually hover it over different components of the connection, and they will highlight. Now, if I click my mouse button and drag it, I can actually rotate this connection around in 3D so that I can more clearly see exactly how the connection has been made. By using my right mouse button and holding it down, I can pan around within the view, and by clicking my center mouse button, I can actually snap straight to an isometric view from whichever other view that I've been in. Now we have a variety of different viewing options that appear up on the toolbar here, such that we can go to an ISO view, a top, side, left, and right view, and we can also toggle between a transparent view to maybe see more clearly what exactly is happening behind that bolt that's been obscured by the angle. So I can click that back and forth to toggle those options back and forth. I can also come into the plot options. Those of you who are familiar with RISA 2D and 3D know this little blue button that's often in the upper left corner, and that controls how we see things here. Now I can turn on rotate view, and the connection will actually automatically rotate around for me so that I can see every angle of it. I'm going to come back in here and turn that option off and hit OK, and I'll hit the center mouse button to snap back to an isometric view. The next thing we can take a look at are the 2D views. You can see we have this layout on the left, 3D view tab, 2D view tab. When I come into the 2D view tab, what we're taking a look at is shop drawing style views of each one of these connections, including the dimensions shown right on screen. So as I click through here, I can take a look at every part and even combinations of parts. And this is where I can see what the dimensions are of this connection, and I can actually control a number of these dimensions just by clicking on them and entering values in. So we have a variety of different 2D views that come automatically with each connection that you can tab between. And all of these are printable as well as the 3D views. And then the last section is the reports. And the reports is where we come in here and we actually see the results for the design. And we can also get a report on all the different members and components that have gone into this connection. So that's just a brief overview. Let's take a look at how we actually work through this connection. So I'm going to come back to this 3D view, and we're going to take a look in the lower right corner. This is where our connection properties are. And this is where we can set everything relating to how this connection is laid out. When I specified that I wanted to create a girder angle connection on here, it automatically created one with some reasonable values input, and now I can actually come through and enter in my real values. So first off, we can choose, as we sort of come down this list here, the connection title we've already entered in. For the girder connection, I can choose whether that's going to be a bolted or welded connection. And I'm going to choose welded in this case. And you note that when I choose that on screen, it actually flips over to show a weld on there instead of the bolts coming through on that girder. So everything is all live updated and is fully interactive. Under the beam connection, for this example, let's go ahead and go bolted. And under angle type, you can choose single or double angle. In this example, I'm going to choose a single angle, and so you'll see that now the double angles that were here before, as I toggle between them, appear or disappear accordingly. And you can also see that the single angle now has a single angle style weld. That is an L-shaped weld that runs down the length and along the bottom, as opposed to solely the vertical weld that you would get on the double angles due to the lack of eccentricity in the plane of the girder. So coming down farther, this is where we specify our shear load. And remember that I set this up in the global parameters as an ASD project. So therefore, when I enter my shear load, it needs to be an ASD load. Similarly, if it were an LRFD project, I would need to enter an LRFD load. So let's enter that in here at 45 kips. And let's come down and choose a girder section and a beam section. So under girder section, you can see one option I have here is to click on this button within the cell, and this pulls up the shape selection dialog, very similar to the other RISA products. And so here I can choose a W24 by 62 girder. And when I hit OK, you may have noticed everything sort of thickened up on the screen here as we got a little beefier beam shown there. Now under the beam section, and this applies under girder section as well, if I don't want to click on this button and go through the whole shape database, I can actually just type in a shape size. So I can type in W18 by 35, caps don't matter. And when I click outside of that cell, it automatically updates, and you see the beam gets bigger and it recognizes what we've typed in. Now we've entered this in, but you'll also want to note that on the left here, we have these little expand buttons here, the plus sign. And when I expand, I can actually control a variety of different additional properties. So you can see that my girders were created as A992 by default. For this example, I'll leave them at that. And then the hole type on the beam is set as standard. So remember that I have to be able to control the hole type on both the beam and the angle separately, because we could have slots in one or the other, or even both. Coming down to the angle section, you can see by default here we have an L 3.5 by 3.5 by 3/8. What I'm going to do is actually pick out a 4 by 3 by 5/16 angle for this particular example. Now the angle material is set at A36, and we have an angle orientation set to SLS, which stands for short leg supported. So the short leg is supported off of the girder here. If I come down a little farther here, under hole type for the angle, I have that set to standard, but let's presume in this case that when it comes to actually erecting this in the field, I'm going to want to have a little bit more play than your conventional standard connection. What I can do is I can come in here and choose short slotted horizontal for the angle type. And if I come to a 2D view of this, and I take a look at my angle, I can actually see that these holes are slightly elongated here. So the program is aware of the actual size, and it's also aware of the design implications that go along with having a short slotted hole as opposed to a standard hole. Coming down a little farther, here we have our girder weld. This is the weld between the angle and the girder. You can see an E70 electrode has been chosen and a fillet weld. And I can control the leg size here, and this leg size is going to be in 1/16 of an inch. And so I'm going to enter this in at 3 for 3/16 of an inch. Under beam bolts, we have listed in here the default bolt is a 3/4 inch A325N. Pretty much the standard bolt. And that's what's been set up here, but if I expand this out, you could see I could actually come in and I could set this in any number of different ways. For now though, let's say that I did have these beams with this 45 kip load. I know I want to do a single angle connection, but that's all I know so far. Well, that's really what the intention of the program is. It's that we set up the very basic geometry for this connection, and then we start making adjustments until we can actually get the entire connection to pass. So let's take a look first off at the 2D views. I'm going to come in here and I'm going to take a look at the beam view to take a look at the cope that we have listed. Now the default cope is based off of a girder beam clearance of 1/2 inch. However, having a cope with 3.31 inches may be a bit impractical. I'm going to round this up to a reasonable number so that there's no difficulties in doing the connection. So if I click on this 3.31, you note that in the bottom right corner here, this cell highlights web cope top length. So we can control things either by changing values in the cells in the lower right corner or by clicking on the dimension up here. And I'm going to type 3.5 and hit enter. And so now the cope expands out to be 3.5 inches. Let me also change the cope depth by clicking right here, and I'm going to put that up to 1.25 inches. So now we've increased the cope depth and the cope length to some values. The next thing I'm going to do is take a look at the beam and angles view, because even though we've dropped that cope down some, the location of the angle relative to the top of the beam still has not changed, and that's set at 1.34 inches. Well, let's say that I want the top of that angle to align with the top of the cope. If I click here, this controls the angle vertical position. And so by clicking here, I can also type in 1.25 inches. And what happens is it becomes 1.28 on the screen. And if we take a look in the lower right corner, that's exactly what's been entered down here. Now, why in this case would it have done 1.28 inches when I explicitly told it that I wanted that to be 1.25 inches? Well, the reason is because of fillet encroachment on the girder. If I zoom in here on my girder and web angles 2D view, you can see that at 1.28 inches, my weld is now touching the fillet radius on the top of that girder. And due to welding constraints, I'm not allowed to weld within the fillet. So therefore, the program keeps me from pushing it up that far. And you'll find there's many other code restrictions that the program is actually taking into account even when setting up your connections. So at this point, we have the basic geometry set here. This is the way we wanted to lay this out. Let's take a look and see how this connection does. To find that, we're going to go to the Reports tab on the left side of the screen. When I click on Reports, the first thing that we see here, because I had tabbed over to it earlier, is the Members Report. And under the Members Report, under Girder, here we get all the information for our girder. The member properties, these came right out of the AISC tables. We get the capacities of it. We get the material on it. The same goes for the beam, the angle, the girder weld, and the beam bolts as well. So we have all this information available. Now, if I go over to the ASD results up here and click on that, I can actually take a look at how this connection did with respect to passing versus failing. This is the screen that you'll spend most of your time in RISAConnection as you go back and forth to try to get your connections to work. So if I scroll through here, what you're going to see is individual limit states listed on the left. So here we have geometry restrictions on the beam. Here we have shear yield of the angle. Here we have the flexural rupture of the coped beam. All of these right here are the relevant code checks that need to be done for this particular connection. And we can see right here, unless specified, all code references are from the AISC 360.05. And we can see on the right here which ones pass and which ones fail. So if I scroll down a little farther, one of the things that I'm going to notice here is that I'm actually getting a bolt bearing failure and a bolt shear failure. And for each one of these, we have the required capacity, 45 kips, and the available capacity, resulting in a unity check, which, if below 1, means a failure. So let's take a look at one of the bad failures that's going on here, such as the bolt shear at beam. This is basically a ratio of 2, so the bolts only have half the capacity that they need. If I click on bolt shear at beam, this drops down and expands so that we can see the formula that was used to calculate this. And what we're going to see here is that the R sub n, the bolt capacity, is equal to the bolt shear stress capacity by the area of the bolt multiplied by the number of bolts multiplied by C. And if we're wondering what is C, we can look right down here and we can see C is the eccentricity coefficient. And that's because the bolts are eccentric to the actual connection. And we can also see that the C used here is a value of 0.71. And here's all the other values that were used in order to calculate this. Now furthermore, if I look over here, I can see which equation was used, J3-1. And if I open up my AISC Black Book and take a look at equation J3-1 in the spec in the back, I'll find this exact equation. So this helps you to see where exactly the numbers came from. It relates back to the transparency that we were discussing earlier. So what can we do to correct this bolt shear at the beam? Well, let me go back to my 3D view at a moment. And you'll see here with this W18, all we have is 3 bolts on here. And that 3 bolts is probably going to be insufficient. If I come to the beam bolts input over here, by default that was set at 3, but I can either choose 4 from the drop-down or type it into this cell. And you can see that now 4 bolts are present. Furthermore, I did not have to adjust the length of the angle. The length of the angle is automatically determined by the bolt spacing and the bolt edge distance, both values that I can enter in the program here. And if I come back to my reports, and now I take a look, my bolt shear at beam, that unity check has gone way down. We're now down to 1.36, but we're still getting a failure. And taking a look at it, one thing that may be having an effect is the fact that we're using the elastic method for the bolt eccentricity calculation. You can see that bolt group eccentricity is calculated at 0.78, and if I click on that, I can actually see exactly where this came from, complete with all the dimensions. Let's go up to the global parameters and the solution tab Instead of using the conservative elastic approach, let's use the instantaneous center of rotation approach. If I click OK on that, we will now see that that bolt group eccentricity coefficient has jumped up to 0.83. So we get a higher value by using a less conservative approach in the program. However, the program does allow you to choose both methods. So with this higher bolt group eccentricity, I now have an even lower unity check. However, we're still not below 1, so this is still failing. Now we can try some other things. Let's change the bolt diameter here from a 3/4 to a 7/8. If I go to 4 7/8 bolts, now we're passing. You can see we have a 0.94 unity check. Everything works out well, so that was evidently what was needed in order to get us to pass. And taking a look at this, we have two things that are still failing here. We're still failing in the clip angle shear rupture at the beam, and we're still failing in the girder weld strength. Now, taking a look at the clip angle shear rupture, this is just a simple shear rupture equation, J4-4, and we can see here that we're taking a look at a net area subject to shear. And so this is the net area of that clip angle. And obviously, the 5/16 thickness on the angle may be a little insufficient in order to handle the amount of shear that we're trying to put through it. So what I can do here is I can actually come in and I can change that to be a 3/8 inch thick angle. And now you can see it passes just fine because the net area subject to shear has been increased. So now everything passes in this connection with the exception of the weld to the girder. Now currently, if we take a look at this, we're using the elastic approach for this method. If I come up to the global parameters here, under the solution tab, I can tell the weld analysis method to also be instantaneous center of rotation. And we'll see as the unity check goes from 1.8 now to only 1.13. A huge difference in the weld between the instantaneous center method and the elastic method. This is why I usually prefer to go with the instantaneous center of rotation method. And we can see that the C, the eccentricity modification factor, is equal to 2.21. Now the formula has been structured in such a way that you can actually go and compare this directly against the tables available in the AISC manual so that you can confirm these numbers if you need to. However, we've set this method up exactly according to the AISC methodology, so the numbers always come out the same. Taking a look at the girder weld here, we've set up a 3/16 weld. We can bump that up to a 1/4 inch weld just by putting it in as 4/16. And when I hit the button there, now we can see the girder weld strength has been increased to 53 kips of capacity, and that's the strength of the weld given or relative to the input. So therefore, 53 kips of capacity, 45 kips of applied load, 0.85 for the unity, and we've passed. So now everything works out for this connection. Now let's say that the other end of this beam is actually going to be framing into a member of the same depth. What I can do is I can come up to the connection up at the top and say create copy, and you can see it's created an identical copy of this connection. And if I click on it, this is called girder angle copy, and I'm going to just come in here and rename this to be girder angle W18. And when I choose that, now I can actually come in here to this identical copy, which we'll see just like the one that it was sourced from passes entirely. And I can actually set this up to have a W18/50 girder. Now this will allow us to find out primarily whether or not the effects of double coping will be critical on this beam. You can see when I set that to be a W18/50 girder, the program automatically copes the beam at the top and the bottom. And if I come into the reports here, I can scroll down, and at a glance, I can see that this passed for everything. So we have nothing to worry about in this particular example. Let's move on to another example. I'm going to come up here within the program, and we're still working within this webinar project, and I'm going to click on this button right up here that looks like a connection. And if I hover over it, we'll see that the button is called New Connection. When I click on it, I once again get my connection browser brought up, and what I'm looking for here is the column beam shear tab connection. And I'm going to click on that right here and hit OK. And so here we have this new connection titled Connection 1, and this is our column beam shear tab. And so I'm just going to set this up. I'm going to call it CS tab. So that way I've given it a name that I can refer back to if I'm trying to move through my Webinar Explorer. However, if I don't remember perhaps what my connection was named, but I remember what it looks like, I can always click up at the top of the Project Explorer here to get thumbnail views of all the connections that are available in my project. So let's come back to the CS tab here. So what we want to do is we want to set this up with a beam connection that's bolted. And then for the column connection, rather than connecting the shear tab to the flange of the column, let's actually come in and set it up to connect to the web of the column. And when I click on web, you can see it flips the orientation such that now we're framed to the inside there. Now for the shear load, I'm going to put a rather large load on here of 100 kips. I'm going to try to challenge the program here by putting in some rather tight dimensions set up for this connection. So under the column section, let's enter in a W10 by 100, a very stout but small column. And under the beam section here, let's enter in a W24 by 68, a very typical girder that would easily be able to handle this 100 kip shear load. And you can see that framing that girder into the web of the column, what we actually have to do is we have to cope the flanges of that girder just to get it to fit in here. Now, obviously, this isn't a condition that we would want to deal with for any sort of new construction, but let's presume that we had to deal with some existing construction. This W10 by 100 column already exists, and I need to bring a W24 beam in to connect to it. How do I do this? Well, one option I have, rather than coping out the flange, is to actually stop the beam short of the flanges of the column and use what's called an extended shear tab. If I come into my 2D view here, and I take a look at my column section, right here, I can get a look at what sort of dimensions I have to work with. So we can see I have 4.81 inches from the face of the column to the tip of the flange. So I want to pull the beam back by at least that much. What I'm going to do is I'm going to come over here to my 3D view, and under the plate section on the right here under components, I can control the width of the plate. The width is how far the plate sticks out of the column. I'm going to enter in 11.5 inches, and you'll see that the plate gets much longer now. And now I'm also free to come in and set my column beam clearance to be 5.5 inches. And when I hit that, that means that the beam will be pulled at least 5.5 inches out away from the column. This allows us to get a connection in here that's going to entirely bypass the need to cope those flanges. Now, the flanges are still going to remain coped currently, but what I can do is come in here under cope dimensions, and I can actually set those all to be 0. All I need to do is set the flange cope width to 0 and the cope length to 0, and that's enough to eliminate that entirely. So now we actually have this plate and this connection all set up. Now, 3 bolts clearly is not going to be enough to handle 100 kips. Maybe we can try 6 bolts, though. And instead of just adding on to the depth of it, what I can actually do is come in here and I can add on to the number of rows of bolts. So I'm going to say I want 3 bolts per row, and I want to do 2 rows of bolts. So now we can set this up like this. Now this connection is going to have to deal with some eccentricity issues, but as you'll see, the program's going to be able to notify us of exactly what those issues are. So with this basic connection laid out, from a visual inspection, I'm sure most of us can look at this and say, no, not going to work. And indeed that is the case. If I come over to the reports, I'm going to find that we actually have more fails than passes on this connection, especially when we come down here and take a look at plate flexural buckling, where we only have 11 kips of capacity for this entire connection. But let's start up at the top here. One of our options is erection stability. If I click on erection stability, what we can do here is we can have it take a look at this condition whereby Ly has to be greater than D minus 2 times K des over 2. What does that really mean? Well, if you take a look in the 13th edition manual, what they say is that the connector must be half the length of the T dimension of the beam, and that's the web dimension from the toe of the fillet to the toe of the other fillet. And in this case, we're just not long enough. Our L-min is 10.76 inches, and our Ly is only 9 inches. So clearly, this is going to be unstable during erection, and this isn't going to be allowed. So what we have to do is come in here and make that plate longer. We could also probably stand to add some more bolts as well, so I'm going to increase the bolts up to 4 bolts times 2. So now when I come back to the reports, my erection stability has been set to pass. Okay, let's take a look at one of the next aspects. For this, I'm going to come up to Tools Preferences, and I'm going to check this box under Preferences that says Check Rotational Ductility for Shear Connections. And if I hit that, you'll see that the erection stability also comes in listed as a rotational ductility check as well. Okay, so we're fine for passing on the rotational ductility. And rotational ductility, by the way, is just the confirmation that what we've designed as a shear connection, that is a simple pin connection, will behave as a pin connection. And that we're also confirming that the erection stability is fine here. If we take a look under rotational ductility, though, I see something odd jumping out at me here. And that is that my plate flexural yielding is set at 0 kips. And if I scroll down a little farther, I can actually see under plate flexural yielding, we're seeing a capacity of 0 kips. This is failing. Well, how could that be? If I click on this to expand this checkout, what we're going to see here is that our FCR, the F critical, for checking the flexural yielding of the plate is at 0. And if you take a look at the formulas that are available for this particular failure mode, you'll find out that the FCR is a function of Fy minus your applied shear stress. And we can see we have a very high applied shear stress. So therefore, the shear stress has reached a point where the flexural yield stress has been reduced to basically 0, and this is through what's known as sort of a von Mises behavior. So one option we have to correct that, because we have such a thin plate on here, is to beef up the thickness of it. That will cut down on the amount of shear stress and therefore allow us to raise that F critical. So under my plate section, instead of going with 3/8 of an inch, I'm going to go with 3/4 of an inch. And we can see that that plate now gets thicker as a result. And if I come back here under my reports, now my plate flexural yielding is looking much better because my FCR can actually be a somewhat reasonable value. But we're still failing all over the place here, especially down here, bolt shear at beam. We've got a 2.88 ratio on that one, and that's going to be insufficient. So if I come over here to the beam bolts, I can change those to be 1-inch bolts instead of 3/4-inch bolts. And now what we're going to see is that the bolt shear is still failing, but it's not failing by as much. Well, maybe if we go up to a total of 10 bolts. So now I have 2 rows with 5 bolts per row. You can see we've almost made it here with the bolt shear to be able to succeed with this connection. And certainly you can see how much is going in to keeping us from coping those flanges. Now definitely you could use this as a sort of value engineering check if you needed to. But of course we'll try to stay away from that term. So if we take a look under set shear load, what I'm going to do here is, because this keeps failing, we're running this in ASD, I might be able to get some additional benefits out of LRFD. So if you recall, when I entered in my shear load earlier of 100 kips, that's an ASD load. Well, let's increase that to an LRFD load. And in this case, I'm going to assume that 50% of the load on this beam came from dead and that 50% came from live. And so if we take a look at halfway between the LRFD factors of 1.2 for dead and 1.6 for live, that would be equal to a factor of 1.4. So therefore, my 100 kips should now be bumped up to 140 kips. And if I come up to the global parameters here under the solution, I can change ASD to be LRFD. And now I hit OK. And now, scrolling down, we're failing by even less because, of course, LRFD can give you some additional capacity when you use it. Now, we're still failing by a little bit here. We got this 1.04, and one of the remaining things that we can do is we can actually come in here and change these to be bolts that are excluded from the shear planes. So we're just going to need to make sure to specify that when we hand this connection out, that they're going to have to basically keep those threads from being in the shear plane. And when I switch this over to be an A325X bolt as opposed to an A325N, now we pass. So we finally got that working. However, now we're failing under geometry restrictions, and we weren't failing there before. And if I open this up, we'll see the reason why. We're doing fine for minimum and maximum bolt spacing and maximum edge distance, but for minimum edge distance, we fail. And the reason for that is because we only have 1.5-inch edge distance, which was set up on the notion of 3/4-inch bolts, but now we've gone to these 1-inch bolts, and they're just going to be too large to work with that 1.5-inch edge distance. Well, I can control that by scrolling down here and actually controlling the beam bolt edge distances that are shown on here. And I'm actually going to come into a 2D view so that we can see exactly where these numbers are going here. If I come in and set this up with a 2-inch edge distance, we can see that now that's controlling the edge distance between the edge of the beam and the edge of the bolts. So these bolts have actually moved back a bit. Let's just go back to 1 for a second here. This is one critical edge distance that a lot of people miss in these connections, is the edge of the beam itself. And then another critical connection here is the vertical edge distance that we're getting on the plates. We want to make sure that that's 2 inches. However, when we take a look at the plate here, we can see we only have 1 inch of edge distance shown on here. And if I click on that 1 and I enter 2, nothing happens. And if I take a look down here, that value is grayed out. Why is that grayed out? Well, there's only one way to control this dimension, and that is by controlling the overall length of the plate. You see, by using the column beam clearance and using the bolt spacing, these values are both hardwired in here. And so what we need to do is come up here under plate section, and we need to tell this plate that it is 12.5 inches wide. And by doing that, the extra inch will be tacked on in the end. So if you do encounter situations where perhaps the value that you want to change isn't directly editable through here, don't get too frustrated, because there's likely another value that's available right above it or right below it that actually controls the overall dimensions of your connection. And I assure you, from my own experience, that once you work with the program enough, you do get a good hang of exactly how to set all the dimensions from every connection, and it becomes second nature very quickly. Now, coming back here to the 3D view, we can see how our layout is now, and coming back to the reports, we're now passing under the geometry restrictions. Now, our column weld strength is failing, and I can see here that we're using the instantaneous center of rotation method. But we only have a 4/16, or in other words, a 1/4-inch weld going to the column. Let's bump that up to a 5/16 weld, and bear in mind this is a double fillet weld because it's occurring on both sides of that plate there, and now we actually pass. Now you might be wondering, what about the base material due to the weld? Well, what we have is a factor called beta in here, and this is the base material proration factor. And if the weld actually gains greater capacity than the plate or the column or anything else that it's connected to, then what we do is we actually reduce the capacity of the weld according to the program so that it matches exactly what the base material is. In this way, you can ensure that you will never accidentally oversize a weld. Now, taking a look in here, what else are we failing on? Well, we're failing under plate flexural buckling. And so here's the formula that comes up with this one. And as we can see, our FCR is only 36 KSI, and we're not going to have an easy time of increasing that, making changes to a number of different things in the geometry of this. Instead, if I really want this to work, my best bet is probably to change the plate section to be an A572 grade 50, a high-strength steel plate. Now has a much higher FCR, and we've almost made it for plate flexural buckling. Now, the plate is still a little bit shallow, but what if I come in and I set the vertical edge distance for the plate, this number in this case, to be 2.5 inches. Now the plate's gotten a little bit deeper, and as a result, it has a little bit more resistance to flexural buckling. As a result, we pass. So the only thing we're failing here is the rotational ductility. Now this is why, if you noticed earlier, I went under Tools Preferences to adjust this. If you actually read the 13th edition, what they say is that the capacity of the welds and the capacity of the bolts needs to exceed both the capacity of the plate in flexural yielding and the bolt bearing capacity. Now what they're getting at here is that the plate should yield either due to bolt bearing or due to flexure prior to the welds failing or the bolts failing. And that's certainly agreeable. If you're going to model something as a pin connection, that should be the case. However, in the program, we found that in practice, it is extremely difficult to get that condition to work out. And sometimes it's just downright impossible. So one thing we do is we give you the capability of shutting that off. If I go under Tools Preferences here, I can actually uncheck the box, check Rotational Ductility for shear connections, so that when I hit OK, this is not listed as failing. Now, it's still up to your engineering judgment as to whether or not that's okay, but what we are allowing you to do is we're allowing you to print out a report that is not going to show something as failing. So if you need to get it through a code official, you can do that. And this is really something very specific to these extended shear tab connections. The rotational ductility does not pose a problem for the other connection types, but I felt I should probably point it out in here. Okay, so now we've got this whole report together. What can we do with this? Well, one option we have is to print the report. And you'll note that we have a print preview available in here. So if I come right up here to print preview, I can see exactly how this report is going to print out here. And so we can see it's going to print out a summary for me exactly like this. Now, if I come up to the Tools Preferences and I uncheck this box that says Print Only Summary of All Design Checks, now, when I go to my print preview, it will actually show me all of the details of every one of these connections. So I can really do it either way, and I can print this out to a printer, or I can print it to a PDF so that I can file this away with my calculations. But you can see how convenient that summary report is, especially for if you have a number of different connections for your project that you need to submit to a code official, for example. Okay, let's take a look at one last connection here. I'm going to take a look at one of the moment connections that we've implemented. So this is the column beam flange plate moment connection. I'm going to create this. I'm going to call it moment. I'm going to hit OK. And so here is this new moment connection that's been created. I'm going to adjust the units in this case because I prefer to work in kip feet rather than kip inches in this particular model. So I'll hit OK, and I'm going to change my shear load over here to be 48 kips, and my moment to be 320. Now remember that we switched over to LRFD in the global parameters, and that is a global setting, so it affects all the connections that are on here. So I need to make sure that these loads are entered in LRFD if that's what I've set there. Now we have various settings for the top column distance, the column force, and the story shear. These all relate to the capacity of the column web due to buckling, crippling, etc. But in this particular example, we're going to assume that this moment connection is occurring at the very top of the column. So therefore, the webs don't extend any further past this plate to allow us to resist a little bit of extra flange crippling in this case. And the column force and story shear can't help us out with regards to the web crippling in this case. Now for the column, let's set this one at a W12 by 96. And then let's set the beam up to be a W21 by 68. That would be a good beam for a moment connection here. And so what we want to do is we actually want to come in here and set this up to be a slip critical connection with respect to the flange bolts. So we're going to assume that for whatever reason in this project, it's extremely critical that there is no rotational slip of this connection. So if I come here to the moment beam bolts, these are the moment bolts put onto the beam, I can actually come in and set these slip critical, and instead of saying no, which is the default, we're going to set this to be a Class A slip critical connection. Now let's come into the reports and see how this connection does. Well, overall, we passed quite a bit, and you'll see there's quite a few more checks here because obviously we have to check for both the moment and the shear in this moment connection. And we're failing for a wide variety of things. And let's see where we're particularly bad is bolt shear at flange plate and beam flange slip critical. So what that tells me is we don't have enough bolts in this case. What I'm going to do is I'm going to change this to be 4 bolts per row on that flange plate. So we bump that out a little bit farther. And let's take a look under the reports here and see that we are still failing for a variety of reasons. We're actually getting a flange plate block shear failure, and we're getting a flange plate tear out failure. What does it mean to have block shear as opposed to tear out? One thing I can do is come up into the help file, and if I take a look under my bolt and material design checks, under block shear, here we get an illustration of exactly what that block shear is going to look like on that flange plate as opposed to the plate tear out. So you can see the difference right here. The plate tear out is failure that's occurring inside of the bolt group, whereas the other failure, the standard block shear, is occurring outside of the bolt group. And I'm failing in both cases in this circumstance. I think it's important that I bump up the width of that plate. Just looking at it in 3D, you can see that we have a lot of real estate to work with here in terms of pushing that out. But how much do we have? Well, it'd be good to know what the flange width of that beam is. If I go to the 2D view, I can actually come in here and I can take a look either at my beam section here, or I can actually, under my reports, just go to the Members tab and take a look at the beam properties rather than having to open up the book. I can see right here that beam has an 8.27-inch flange width. And so I can come in here and control that moment plate section, and I can bump it out to be an 8-inch width section. Now, we've pushed that out there, and you can see the bolts have sort of moved out with it, so now we have a more reasonable looking plate. But we're probably still failing in here. And yes, indeed, for bolt shear, we're still failing. Let's try going up to 5 bolts. So now we've got 5 bolts per row on there, and we're still not quite making it. And you can see that we're also failing in flange plate tension yield. So that plate's actually failing in a yielding. What I can do here is come up, and I can change the thickness of those flange plates to be 7/8 of an inch. So that's 0.875 inches. And there you can see we've actually thickened that up. Well, we're getting closer here, but we're still failing. I can see that we're failing in the welding that's going on here. The weld strength has failed. So maybe instead of going with these double fillet welds that we've placed on there, let's come in here to moment column weld, and let's change that to be a partial joint penetration weld, a PJP. And let's try giving that a 5/8-inch effective throat. So we've got a pretty decent PJP weld on there. And how's that going to work out for us? Well, under flange plate weld limitations, we're getting a failure here. And if I come down a little farther here, under flange plate weld strength, we're still failing. And so obviously the capacity of that partial joint penetration weld just isn't quite enough. Well, let's flip it instead of being a PJP to a CJP, a complete joint penetration weld. Now I can see that we are actually passing for that weld. So everything's all set with that. Okay, the moment bolts are still not working. Let's try putting those up to be 1-inch bolts. And so now the only thing that we're failing at is geometry restrictions at the flange beam and the bolt shear at the beam web. Now, that's the number of bolts that are actually occurring at the web. That's very easy to bump up. Those are just the beam bolts as opposed to the moment beam bolts. So now we pass with that. And coming up here under geometry restrictions at flange beam, now we can see we're failing due to edge distances once again. So now I need to set those moment bolt edge distances out so that we have a little bit more to work with because we have these 1-inch bolts. So I'm going to go to the moment bolts edge distances. Now I'm going to set these to be 1.75-inch for all of these. And you'll see on screen exactly how this affects things as I change these values. You can see it pulled the plate out and it pushed the bolts in closer to each other. Excellent. So now we're passing on everything except for column flange bending, yielding, and web crippling. Well, these are your standard column localized failures that many of you are probably familiar with, and typically you would fix these with stiffeners and doubler plates and such. Well, currently, RISAConnection does not have the design of stiffeners and doubler plates. We had wanted to get it into Connection 1, but the amount of demand to release RISAConnection meant that we had to release it before we could get it in there. But we do plan on getting the design of stiffeners and doubler plates into the program, so don't worry about that. In the meantime, what you can do is you can actually use this to do what amounts to be a clean column check. We can try bumping up this column size, let's say to a W12 by 120, to see whether we can get rid of the need for those stiffeners and the such. And so we can see here column flange bending still fails by a little bit, but if I go up to a W12 by 136, I'll probably find that's not a problem. And if I have a variety of conditions where this is happening within my building, what I'll probably find is that going from a W12 by 96 to a W12 by 136 actually ends up saving a lot of money over all the welding of those web doublers and stiffeners. So that's one thing to definitely consider. All right, at this point, I'm going to start to wrap things up because I can see that we're approaching the end of the hour. And so I'd like to talk about what's next for RISAConnection. So RISAConnection version 1 does not integrate with RISA 3D and RISA Floor. However, we've already begun work on RISAConnection version 2 that will be fully integrated with both RISA 3D and RISA Floor. And for those of you who are purchasing the program or thinking about purchasing the program, you should be aware that by buying RISAConnection, you are automatically entitled to RISAConnection version 2, which is fully integrated. So don't feel that you're going to be left out in this. This is actually part of our long-term development plan, and everybody who purchases the program will get RISAConnection 2 next year when it comes out with that full integration built in on it. Now, I'd also like to direct you over to our website, and I'm going to bring that up here. If you come to our website, risatech.com, and go under Products, you'll see we now have RISAConnection listed on the Products page, and we have a link right here where you can download a demo version. So you can actually download this and try it out yourself to see how it works. And if I click on this, we also have additional information. We have another video showing how to use RISAConnection, very similar to what we've just covered here. And then we also have some introductory pricing available for RISAConnection as well. So if you click on this, you'll see that we're actually running a $200 off special for the remainder of the year. Now, for those of you who already own RISAConnection or who have already purchased it, we will be sending emails out later on today with links to download and install that software. So today is sort of the first official release of RISAConnection, and I hope all of you have enjoyed it and have enjoyed seeing the capabilities of this program that has really, sort of revolutionized the way the RISA interface is set up and is really going to move forward at a very fast pace. So the additional resources available are the RISAConnection help file and the RISAConnection general reference manual, and then, of course, our website. And if you have any questions, just let us know as shown on here. Once the webinar is closed, we'll post all the Q&As right onto our risatech.com website.